let's take a look at how to find the determinant of a matrix. Now remember, a matrix is just a box that's holding numbers for us, is one way to think about them. The determinant is just a number associated with a matrices. The way that you want to think about it is, I guess a little bit later on, kind of like the, if you think about it in terms of vectors, the magnitude of the matrices. It's not quite that, but it can be kind of associated with that. It's like a scaling factor. Let's just see how to do it. Now the first thing, you can only find the determinant of a square matrix. Non-square matrices do not have determinants. So let's start out with a very simple definition. If we have the smallest, except for a 1 by 1 square matrices, the determinant of a 2 by 2 matrices is you multiply down the main diagonal, A times D, minus you multiply down the off diagonal, B times C. So by definition, this is the determinant of a 2 by 2 matrices. For any other square matrices, any larger, 3 by 3, 4 by 4, so on and so forth, we're going to use a method called expansion by cofactors. Now, scary names, and if I tried to write the steps down for you, it would be very, very confusing. It's actually pretty easy to do. So we'll get to this definition in a second. I'm just going to go ahead and put, say, 3 by 3 matrices up here. 1, 2, 3, 2, -1, 5, -3, 2, -4. All right, so there's a 3 by 3 matrices. Now, expansion by cofactors means we're going to expand this matrix across either a row or a column. And you can pick any one that you want. The method's the same. Now, I need to change my notation here a little bit just because I don't feel like writing the whole thing again. When we have the square brackets around it, this is a matrices. If you change the square brackets to straight up and down lines, that means we're looking for the determinant. And hence, kind of like the magnitude of a vector or the absolute value, it's kind of talking about how big something is, kind of. All right, so just for the sake of this particular problem, I'm going to expand across the first row. Now, I'm going to say this isn't a sentence, and then I'll show you how it works. So what we're going to do is for each position as we move across this row, there's a value in that position, there's a sign associated with that position, I'll talk about in a second, and then there's a determinant you get if you cross out the row and the column of that position. All right, pretty scary. So let's start. The first thing you need to know is the sign matrix. This is just a matrix, again, a square matrix of any size that you need. Starts with positive in the top left, and if you move vertical or horizontal, it alternates in sign. So positive, negative, positive, negative. So by looking at this, you can see you've kind of overlaid this. Each position has a value in that position and a sign associated with it. So let's say we were going to expand across the first row. We're going to multiply the sign of that position, that's a positive, times the value in that position is a 1, times the determinant you get if you crossed out the row and the column the 1 is in. So if you crossed out the first row and the first column, you'd end up with this little 2 by 2 right here. You'd end up with -1, 5, 2, -4. Okay, so this is the value we're going to get from the first position. Now we do the same thing for every position and just sum it up. So then we add. Let's go to the second position. Second position, according to our sign matrix, has a negative associated with it. So there's a negative there. The number 2 is there. And then the matrices we get if we cross out the first row and second column. So if we cross out the first row and second column, we get these 4 numbers. So that's 2, 5, -3, -4. Plus, moving over to our last position, the 3. According to our sign matrix, that's a positive position. There's a 3 in that position. And if we cross out the first row and third column, we end up with these 4 numbers. That's 2, -1, -3, and 2. All right, so now what we got to do is kind of clean this up. So let's see. First, positive times 1, positive 1 is still just a 1. Now we know how to do the determinant of a 2 by 2 by definition. You multiply down the main diagonal. So -1 times -4 is +4, minus multiply it down the off diagonal, 10. All right, so we got a positive, negative, and a 2, so that's going to be minus 2 times. Multiply down the main diagonal, that gives me negative 8, minus, multiply down the off diagonal, negative 15. So we got plus 3, so plus 3. 2 times 2 is 4, minus negative 3 times 1 is 3. So it's all over but the arithmetic now. So that's 1 times negative 6 minus 2 times what's this going to be? Well, let's go ahead and write it out. Plus 15 plus 3 times 1. So that's negative 6 minus 2 times 7 plus 3. Negative 6 minus 14 plus 3 is negative 17. Okay, so the determinant of this 3 by 3 is negative 17, I hope. So, if you want to do a quick check to see if you understand the method, go through here, pick another row or another column, I don't care which one you pick, and see if you can expand across that, and you should end up with the same negative 17. Doesn't matter which row or column you expand across, you should always get the same value for the determinant. Now, where this does get more and more complicated and much more work is the larger that this matrices gets. The method's the same. So if this was a 4 by 4 and we wanted to expand it across the first thing, this would still be a positive position of 1, but the matrices we get once we cross that out would be a 3 by 3. And we'd have 3 by 3s you'd have to do. For each one of those 3 by 3s, you'd have to do this whole method. So a 4 by 4 has 4 3 by 3s, and each one of those 3 by 3s has 3 2 by 2. So you see, it gets really big, really fast. And even for a computer, this gets out of hand really quick. Now, finding the determinant of matrices is a skill that we're going to need throughout our math career, so make sure that you're practicing. It's really not that hard. Careful with the arithmetic, though.